Okay, everybody. Sorry to start off this video. I need to plug in my iPad, I just realized. So this is the video for Tuesday, September 27th's lesson. For anyone who's absent or for our volleyball players who have to miss for a game, hopefully this will just give you a chance to see what you missed. We'll try to get through this as fast as possible. So we're going to start off the lesson with reviewing domain and range for some of these graphs. This is in our packet. I'm probably going to have people in class try these first before I go through them, but you can just watch the video. I would recommend, if you feel like you know how to do these, to try to put your answers down first and then look and see what, then watch the video and see what I got, and then compare your answer. So remember, domain is the set of all x values that our graph exists for, and the range is the set of all y values that our graph exists for. And we always go from small to large, so it's always small values first. So we go small to large, and then large values last. Now for domain, the smallest x values are on the left, and the largest are on the right. So domain goes left to right, and the range, again, if we're going small to large, if range is the y values, then we go bottom to top. The smallest y values are at the bottom of our graph, and the largest are at the top of the graph. So, and then don't forget, we use parentheses if we don't include a number, and we use a bracket if we do include a number. So for number 1 here, the set of all possible x values, think farthest left x value, well, that's this point right here, and the x value there is, let's see, 1, 2, 3, 4, 5, 6, -6, and since it's a solid dot, we use a bracket. So I've started with the smallest x value, or the farthest on the left. Now I want to write the largest x value, or the farthest on the right, which is based on this point, which looks to me like probably +6, 1, 2, 3, 4, 5, 6, and it has an open or hollow dot, so we use a parentheses to show that we're not including it. And that's our domain. The range is the same thing for the y values. Think, what's your lowest point? Well, the lowest point on our graph is right here, and the y coordinate for that is a 1. And since it's a hollow circle, we use a parentheses for that. Then ask yourself, what's the highest point on our graph? I would say that's right here. And that y value looks, I'm guessing 6, 1, 2, 3, 4, 5, 6. And since it's not a hollow or open circle, we use a bracket. And there's our domain and range for number 1. Number 2 is a very similar idea. Again, domain, go from left to right. The left point is right here, and that x value is -5. Since it's a solid circle or not hollow, it's a bracket. Then we want to give the farthest right point on our graph, which is right here. And that's the x value of that point is 1, and since it's a hollow circle, we use a parentheses. There's our domain. Now range, we use the lowest y value. The lowest point is right here with a y value -5, and it's a hollow circle, so we use a parentheses. And the highest y value, or the highest point in our graph, is this one, and it has a y value +1, and since it's a solid dot, it's a bracket. And there's our domain and range for this one. So domain and range we did cover last week, so this should be mostly review. Hopefully you can look back over last week's notes if you need help. So number 3 is different from the first two because we have isolated, distinct points here instead of a collection of points. So just to be clear, when we have something like this where it's a line that's connecting everything, we have points. We have points literally everywhere on this graph. So let me change colors here. We have a point right here, we have another point right here, another point right here, another point right here. Technically, when we connect a line like this, we're saying there's an infinite number of points that we're connecting through. Now in number 3, there are not an infinite number of points. We're not connecting these spots with lines, so there are not an infinite number of values here. We have, let's see, however many points we have, 6 separate distinct points. So this is an example of discrete data. We'll talk a little bit more about discrete data in this video, I believe, here. We did mention it last week, too. But number 3 is an example of discrete data, and number 1 and 2 are examples of continuous graphs or continuous data. And we write the domain and range separately, or in different ways for these. In number 1, we use this interval notation if it's continuous data, and we use something called roster notation if it's discrete data. Because technically, if we're writing with interval notation, we're saying it's every single value in between these, the infinite number of values that are in between -6 and 6, and in between 1 and 6. There's an infinite number of numbers in between those. But for discrete data, we don't want to include all the numbers between these. We want to include just the specific x and y values. So how do we do that? Well, we use roster notation. Roster notation means we're basically listing numbers inside of braces like this. So we use braces for discrete data. Again, the one on the left, the way I draw it, is it's an S, and then, okay, so I have to go very carefully. It's an S, and then I draw a 2. Okay, it's kind of hard on here. And then I draw a 2. That's how I draw the first one. An S, and then a 2. And the one on the right is a 2, and then an S. Doesn't have to be perfect, but that's kind of what helps me write them. So we are still going from smallest to largest x values for domain, which means we're going from the left to right on our points here. So you start with a brace, and I would say the farthest left point is the one right here, and that x value looks to be like 1, 2, 3, 4, 5, -5. The next point on the left would be this one, and its x value is -2. And hopefully you get the idea. We're just writing all these out, separated by commas, going from smallest to largest, or left to right for the domain. The x value of this point, which is the next point on the left, if we're going from left to right, is 0. Then we have this point, which is x, which x value is 1. Then we have this point, which has an x value of 5. 4, sorry. 1, 2, 3, 4. And the farthest right point is this one, and it has an x value 1, 2, 3, 4, 5, 6. And that's our domain for this one. Now we just do the same thing for range. So again, we're using braces, and we're going from lowest to highest, from bottom to top. So the lowest point is this one, and its y-coordinate is 1, 2, 3, 4, -5. Then I'm going to go to the next highest point, which is this one. And I want to read that y-coordinate, which is -2. Okay. The next point up is this one, which has a y value -1. Now we have an interesting thing happen here. We have 2 points that are the same. Like if you're going from bottom to top, these two are tied. So we write the y-coordinate for these, but we don't repeat them. So they both have a y-coordinate 0, but I don't write 2 zeros. I just write it once. And then the last one, this is the uppermost point, or the one on the top, and its y-coordinate is 1, 2, 3, 4, 5. And so that is our domain and range for number 3. That's how you do domain and range for discrete data. This is called roster notation. So this is roster notation, and this is interval notation. These are notations that don't really work for the other cases. You can't use interval notation for discrete data, and you can't use roster notation for interval notation, or for continuous data. Because continuous data, we're technically saying an infinite number of values, and it would take you a long time to write an infinite number of points or values separated by commas, right? So these two notations are good for their own specific data type and not really for the other one. All right, let's keep going here. So I'll just go through a list a little bit faster. The domain for this should be everything from -infinity to positive infinity, because it goes to the left forever, and it goes to the right forever, and everything in between. Now the range is different. We're going from smallest y values to highest. The lowest it goes, well, if these arrows point down, it goes all the way to negative infinity. And the highest y value, the highest point in the graph, is this one right here, which has a y-coordinate 3. And since it's not an infinity or a hollow dot, we use a bracket on that. All right, number 5, we did one similar to this in class. This arrow goes left forever, this arrow goes right forever, and it's connected with everything in between. So we write this for the domain. You could also, when it's like this, it goes left forever and right forever and everything in between, you can say all real numbers is another way of saying this. And even another way is this fancy looking R with a double line. That also means all real numbers. So these are three different ways of saying the same thing. And actually, our range would be also this, because there's an arrow going down forever, there's an arrow going up forever, and everything in between, so we have the same thing. I'm just going to be sticking with interval notation, but again, you could say all real numbers or that fancy R, and that would mean the same thing. Number 6. Again, hopefully you're trying some of these before you just watch me do it. The domain, we want to go left, farthest left. Well, that arrow goes left forever, so that goes all the way to negative infinity for x values. And then we need to write the largest or farthest to the right. Well, if there's an arrow going right forever, then that goes to positive infinity. So again, you could say all real numbers here. The range is not this, though. It's going to be different from our domain. Think, what's the lowest point in our graph? Well, I would say that's right here with a y-coordinate of 0. And since it's not a hollow dot, use a bracket to show we're including it. And then we want to give, since we used the lowest point, now we want the highest or uppermost point, the one on the top. And if we have arrows going up, it goes up forever. So if it goes up forever, it'll go to positive infinity. And we close that with a parentheses. You can never reach infinity, so we use a parentheses on those. And that's a quick little recap of continuous data, discrete data, and domain and range for those. Okay? Again, we did some of these in class on last week. I'm trying to remember which day it was. I think it was last Wednesday and Thursday. We did some of these. You can look back to those notes potentially. Now we're going to jump into new stuff, and actually the pages are out of order here, so we'll start on this page. Start with this should be the first page for this unit, or this lesson. So we have linear and nonlinear functions. We want to write down a few things in here. So you want to write small more than likely. Linear functions have graphs that are straight lines and other things to be aware of. X and Y values change at a constant rate. X and Y values change at a constant rate. Variables are not squared. So this is going to be a long sentence, right? Variables are not, variables do not have exponents. Technically, it's exponents other than 1, which are exponents we do not write. So they don't have exponents other than 1, which we don't write. Again, so x is the same thing as x to the 1 power. So if it has an exponent other than 1, or one that's not written, then it's not linear. So variables do not have exponents other than 1. Variables are not inside roots or radicals. So I'm talking about square roots there. A square root is called a radical, or sometimes we just call them roots. So you can't have a variable inside a root or a radical. Variables are not in exponent locations. Variables are not in the bottom of a fraction. I'm trying to think if there's any other cases to mention here. So they don't have exponents other than 1. Their variables are not inside roots or radicals. They're not in exponent locations, and they're not in the bottom of a fraction. Let me take a quick look to see if I'm missing anything else. No, that's pretty much it. So we'll put a period at the end of that. And then some examples. You could have like y equals 2x, y equals x plus 7, y equals negative x plus, let's do minus 10, y equals x over 4, that's still linear, y equals 2x plus 3, so those are all cases of linear ones. We'll maybe have more to add after that, if I think of more. Those are stuff we want to write for linear functions. If you don't have room to write all that, just get the 3 bullet point things I wrote down. Nonlinear functions have pretty much the rest of these things. Graphs are not straight lines. X and y values do not change at a constant rate. Oh, I just realized I'm not wearing my headphones, so the tapping might be really annoying. I'm sorry about that. I don't have my headphones. I don't know where they are. So yeah, I'm sorry for that. I'll try to remember to use them for the next video I do. And then, obviously, I'm not going to write that whole sentence out, but variables can have exponents. So something like this could be like y equals x squared, or y squared plus x squared equals 2. You can't have things inside a square root. You can't have a variable inside a square root. You can't have a variable in the exponent. So like 3 to the x power, you can't have something like that. We don't want variables in a fraction or in the denominator of a fraction. So something like 4 over x is not okay, but you could have x over 4. So again, the variable can't be in the denominator. That's pretty much it for now. So let's go through these, and let's decide whether these things are going to be linear or nonlinear. So with the 2 graphs we have here, we can tell the first one is nonlinear because it's not a straight line. The graph is not a straight line. And the second one is linear because the graph is a straight line. Okay. So that's easy to tell with a graph, but then we have this table, these tables of values, and we want to decide if these are functions, not functions, linear or nonlinear. So there is a way to tell. Obviously, we could plot these points in a graph and check. So let's do that really fast. I'm not going to do this for all of these, but you could do this yourself to prove it to yourself. You can open up Desmos.com. So this is actually a Desmos app, but it almost looks identical. You go to Desmos.com and click on, I think it's Graphing Calculator. It's like the main button on that page. It'll take you to this. Once you're here, you can hit the plus sign and hit Table. And now we can type in our table values. So our x values are 3, then 6, then 9, then 12. It's actually auto-filling this in for me. And then just be careful of that, because it's actually assuming that the pattern's going to continue, and that's only going to happen for linear ones. So then our y values are 36, then 30, then 24, then 18. And these points do appear to be on a line, a straight line. I can't draw it on here, but they do look to be on the same line, on a straight line. So I would say probably seems like it's linear, but we can prove it to ourselves without having to look at a graph. And to do that, we look at how the x values are changing and how the y values are changing here. So if you look from here to here, it looks like the x value is getting bigger by 3. At least from those 2 numbers. Now let's see, from 6 to 9, it looks like it's also getting bigger by 3. From 9 to 12, it's also getting bigger by 3. So let's see if the y values are changing at the same at a constant rate as well. So from 36 to 30, the y value is dropping by 6 or decreasing by 6. From 30 to 24, it's also decreasing by 6. And from 24 to 18, it's also decreasing by 6. So this is linear. So this is linear because the x and y values are changing at a constant rate. Okay, so let's take a look at these next couple of examples. So again, let's see how the x and y values are changing. It looks like the x values are getting bigger by 2. And the y values, so from 2 to 9, it's getting bigger by 7. From 9 to 20, it's getting bigger by 11. And from 20 to 35, it's getting bigger by 15. So there is, it does look like there's a pattern here. The y values are getting bigger by 4, but they're not changing at a constant rate. So this is nonlinear. So this is nonlinear because the y values are not changing at a constant rate. Even though the x values were. So that's nonlinear. We'll do the same thing for this last one. Why don't you try this one on your own? Maybe pause the video. But I'm going to assume you've paused it and keep going. So our x values from 0 to 1, that's getting bigger by 1. From 1 to 2, getting bigger by 1. From 2 to 3, still getting bigger by 1. So the x's are changing at a constant rate. For this to be linear, the y's also need to change at a constant rate. It doesn't have to be getting bigger by 1, but they have to be changing by changing by the same thing every time. So here, we're adding 10, but then it looks like we add 20. I don't even need to see the last one. As soon as I see that it's not always the same thing, I know it's nonlinear. Okay? And it'd be basically the same reason as the second one. So now we have these examples at the bottom. Why don't you take a second to decide if these would be linear functions or not? Again, maybe pause the video, just under each one say linear or nonlinear, and pause the video, and then try them, and then you can resume the video and see. Okay, so this one would probably be easiest to get rid of to say which ones are nonlinear first. So this second one is nonlinear. The third one's nonlinear. So the second one's nonlinear because we can't have a variable inside a square root. The third one's nonlinear because we can't have a variable in an exponent location. This fourth one is also nonlinear because we can't have variables in a denominator. And the last one is also nonlinear because you can't have variables with exponents written on them. So specifically this 2 here, oh, did not mean to do that. This 2x, what the heck? All right, I don't know why that's happening. Okay, it's going to keep happening apparently. I have no idea why it worked that time. Anyway, as soon as you have a variable written on an exponent written on a variable that's not 1 or not an unwritten exponent, it's nonlinear right away. So if you might be saying to yourself, well, this y equals 6 times x minus 1 doesn't really look like the example that we wrote above. But if we distributed this through, we'd get y equals 6x minus 6, and that would be linear. Notice we have, it does look like the examples we wrote above, but we don't have any variables that are being inside a root or in an exponent location or in the bottom of a fraction, and they don't have any exponents written. This first one is technically a constant function. I'm pretty sure, I'll have to double check, but these are typically kind of lumped together with linear functions because they have a straight line graph. So it kind of depends what definition we're using, but I'll have to double check before we meet again, but I'm fairly certain we're going to be considering these linear functions based on our purposes. If you go really into the nitty-gritty details, it's not technically a linear function, it's a constant function, but for our purposes, it does kind of check all the boxes. So we will just, for now, assume it's linear, and we'll talk more about it later. So we have one more page to talk about, which is this one. So this is where I'd probably have people try these on their own. You could type all these into Desmos.com as the equation or the graph and decide if they're linear or not. So at this point, you could pause the video and attempt these on your own, and then resume the video and watch. I'm probably not going to do these in order. I'm probably going to do the two graphs first, then the two equations, and then we'll talk about the tables after that. I'll probably go from the bottom up and on this sheet. So pause the video and try some of these on your own. Okay, hopefully you've tried those 8 problems. Number 7 is nonlinear. So I don't like how the end looks. Nonlinear, because the graph is not a straight line. So we'll just be very, very brief, not a straight line. Number 8 would be linear because it's a straight line. Okay, number 5, you might be saying it doesn't really look like the other ones because y is not alone. Well, we could move the 5 over if we really wanted to. You don't have to do this to decide if it's linear or not, but it might look more like the examples we wrote before. This would be an example of a linear graph. It meets all those requirements for what we've said, or if you were to graph this in Desmos, it's a straight line graph. Number 6, as soon as you see an exponent on a variable, it cannot be linear. So this is nonlinear. You could say you graphed it and notice it's not a straight line, or you could say a variable has an exponent. Has an exponent that's not 1. So again, this y technically has an exponent, but when it's not written, it's an exponent of 1. And that's okay for it to be linear and have exponents, but you can't have an exponent that's not 1 for it to be linear. Okay, so these tables, again, you could plot these points and see, does it look like they line up on a straight line? If so, linear. If not, not linear. That's one way, but let's go through and hopefully not rely on that because we're not always going to have Desmos available to us. And let's go through the way where we're just checking how the x and y values change. So, looks like the x value is getting bigger by 1 for all of these on the left. Typically, the x values do follow the pattern. It's the y values that might not, but that's not always the case. So you should just be checking both every time. Looks like the y value is getting bigger by 3 here, then getting bigger by 3, getting bigger by 3, getting bigger by 3. So this one is linear, and the reason is constant change. Constant change for x and y. Okay, so let's do the same thing for numbers 2, 3, and 4. Looks like the x value is getting bigger by 2 in this one, and that's for all of them. It looks like it's getting bigger by 2. And then the y value starts off getting bigger by 1. Oh, but then it gets bigger by 2. I can automatically here say it's not linear. But I can keep going and realize, yes, the y values are not constantly changing. So this is non-linear. And then not a constant change in y. Okay, number 3. So getting bigger by 1, getting bigger by 1, getting bigger by 1, getting bigger by 2, getting bigger by 2, getting bigger by 3. So this one is nonlinear for the same reasons as number 2. And then for number 4, x is getting bigger by 4, getting bigger by 4, getting bigger by 4. Y is getting smaller by 2, smaller by 2, smaller by 4. So again, This one's also nonlinear because it does not have a constant change in y. Okay, I'm probably going to have to stop the video here in a second. I think that we're going to do this one in class as well, if time allows. I'm not really sure if we're going to have time or not. But this does cover stuff we've already mentioned. Remember, so the first blank here is discrete. A discrete domain is a set of input values that consists of only certain numbers in an interval, not all of them. It gives us an example on a number line right here. And then a continuous domain is a set of input values that consists of all the numbers in the interval. So you can graph these, and in this first example, when they're talking about each customer, the number of the inputs be the number of people. So you could have like 0 people show up, 1 person, 2 people, 3 people, 4 people. You can't have this one is going to be discrete because you can't have a fraction of a person. So you have to figure out their outputs and then plot the individual points and use roster notation for the domain. For this one down here, we're talking about the number of calories burned. So you can talk about if you find how many calories if you eat 0 bars, then 1 bar, then 2 bars, 3 bars, 4 bars, and just know that when you plot these points, it is possible to burn part of a calorie. Like you can burn 3.5 calories. So your graph for this one will be continuous. Okay. So that's our notes for this. You do have 2 IXLs to go with this. Let me just double check which ones they are. And they are in your recommended list as well. So the 2 IXLs you were supposed to do are Q5 and Q6. Again, Q5 and Q6, both with a score of 70 or higher by Sunday at midnight. Hopefully this video helps. If you have any questions or concerns, you can just email me or talk to me in class when you're back in class next. But hopefully this helps you avoid from falling behind. All right, good luck.